This is 11.10, Taylor and Maclaurin series. So far we've been talking about different types of series and power series that we can represent as functions. And now what we're going to try to do is we're going to try to express or try to express any function as a series. So I guess the question here is, can you represent any function as a series? Okay, so that is basically the main $1,000,000 question. We saw that we can represent 1 over 1 minus x as a series, and also certain certain types that look kind of like 1 over 1 minus x. But can we represent any type of function as a series? Can we represent an e to the x or a sine of x as a series? Okay, so one of the things that we're going to do is that we're going to start off with the more general power series. So c sub n x minus a to the power of n. So we're going to try to represent this a little bit. So let's go and let's say that this is our function. Okay, so this is the function that we're going to try to represent. So let's assume that we can represent it like this. Okay, so let's see what would happen. So let me go ahead and just expand all of this. So I plug in 0, so I'm going to have c0 x minus a to the power of 0 plus c1 x minus a to the power of 1. Then I'm going to plug in 2, c2 x minus a to the power of 2. Then I'm going to plug in c3 x minus a to the power of 3, and then it just keeps going. Okay, and we know that the radius of convergence x minus a has to be less than r. Okay, so now what we're going to do, notice that f of a is going to be equal to c0, because if I did this, this thing is just going to be equal to 1. So c0 plus c1 x minus a plus c2 x minus a squared plus c3 x minus a cubed, so on and so forth. If I were to plug in a, all of these guys are going to cancel out, and I'm left with c0. So f of a is equal to c0. Okay, so now what I'm going to do, what I'm going to try to do is I'm going to try to figure out what all of these coefficients are. So I already know what f of a, what c0 is. c0 is going to be f of a, plugging in a. So what I'm going to do, I'm going to take the derivative of this function, okay, f prime. So what's going to happen, this thing is going to go away. I'm going to take the derivative with respect to x for this guy, and I'm going to be left with c1, okay? Then in my other one, take the derivative of this, I'm going to move it over, so I'm going to have 2c2 x minus a. Take the derivative of the second one, and I have 3c3 x minus a squared. And if I keep doing that, I'm going to have 4c4 x minus a cubed, and so on and so forth. Okay, so I'm going to plug in x equals a. If I plug in x equals a, well, what's going to happen is that this guy's going to go away, this guy's going to go away, this guy's going to go away, and so on and so forth. So that means that when I plug in a into the derivative, I'm going to get c1. Interesting. So I got c0 by plugging in regular a into the function. I got c1 by plugging a into the first derivative. Okay, so let's take the second derivative. Okay, the derivative of c1 is just going to be 0. Then I'm going to take the derivative of the following one. It's going to give me 2c2. Okay, then the next one, I'm just going to leave it as is. Okay, so I'm going to move the 2 over, so I'm going to have 3 times 2, then x minus a to the power of now 1. Then I'm going to move the 3 over, I'm going to have 4 times 3, c4 x minus a squared, and so on. Okay, I'm going to plug in x equals a again. Well, when I plug in x equals a again, I'm going to get the second derivative. When I plug in a, I'm going to get 2c2. Okay. Let's take the third derivative. Okay, maybe we still don't know what the pattern is. We're going to try to look for some pattern. Okay. So I'm going to take the derivative again. Okay, so now this guy's going to go away. And now I'm going to take the derivative. The one is just going to be, let me write 2 times 3 c Oh, I forgot the C3. C3, okay? And then the next one's going to be, I take the derivative of that, is going to be 2 times 3 times 4, x minus a. Then if I keep going, it's going to be 3 times 4 times 5. I keep forgetting my c's. C4, C5, x minus a squared, and I keep going, okay? And again, if I plug in x equals a, what I'm going to have is that the third derivative, when I plug in a, I'm going to get 2 times 3, C3. Well, actually, this is just the same thing as saying 3 factorial C3. This is the same thing as saying 2 factorial C2. This is 1 factorial C1. This is 0 factorial C0. Okay, so basically the pattern here, if we look at the pattern, okay, the nth derivative, okay, whatever this is, the nth derivative of when I plug in the value of a. So if I were to take the derivative of this n different times, and I plug in a, what I'm going to get is 2 times 3 times 4, all the way until I get to n cn, which is basically n factorial cn. Okay, so I know that the nth derivative, when I plug that in, is just going to be equal to n factorial times the constant. So how can I figure out what the constants are? The constants is just going to be equal to divide n factorial over the nth derivative at a divided by n factorial. Okay? Okay, so if you got that, that's great. If you didn't, don't worry about it. This is what I want you guys to really know. This is really important. So, if, write it over here. If f has a power series representation, okay, and we're going to call this expansion at a, then this f of x is equal to the sum from n equals 0 to infinity c sub n x minus a n, okay? Which is basically what we started off. This is what we assumed, okay? Then its coefficients are given by c sub n is equal to f, the nth derivative of f, plug in a divided by n factorial. So we're going to plug this into c sub n. So f of x can be represented as a series by just taking the nth derivative, plugging in the value of a that you like, x minus a to the power of n over n factorial. So if I were to expand all of this, this is basically what you're doing. You're first starting off f of a plus f prime of a over 1 factorial x minus a plus f double prime a over 2 factorial x minus a squared plus f triple prime a over 3 factorial x minus a cubed, so on and so forth. This thing is what we call Taylor series. Okay, which basically means that I am representing a function with the series. And this is super powerful because if I can find a closed form of a function, okay, then I can easily program this using a programming language. Okay, I can program a function using a programming language, loop it around, and then are able to figure out what the function value is going to be, okay, at some particular value of x, okay, provided that you do have convergence, okay, for this part, okay. So what this is saying is that you can kind of represent all of these functions as series, okay, which is actually really cool. And that's basically how your calculator works. And how does that work also? Well, I mean, let's say, for example, you wanted to find the integral, a really complicated integral, like the integral of, I don't know, cosine of x squared, something like this. Well, if I can try to relate cosine of x squared to a series where I'm only looking at polynomials, because polynomials are easy, and I can represent this thing with a polynomial, then this integral is going to be really easy to solve because all I'm really looking at is just x. Okay, so this actually is going to be really, really useful, especially if you want to find approximations to really complicated integrals. Okay, so these are Taylor series. Okay, these guys are Taylor series. We do have a special kind of series, and we'll finish this video with this one. And here's a special case. So the special case is when a equals 0. So if you want a to be 0 in particular, is what we call Maclaurin series. Okay, and what Maclaurin series says is that you have f of x is equal to the sum from n goes from 0 to infinity of the nth derivative evaluated at 0 over n factorial x to the n. So basically, instead of having an a in here, you're just going to plug in a 0. So you're going to have, have f of 0 plus f prime of 0, 1 factorial x plus f double prime of 0 over 2 factorial x squared, and so on and so forth. So in the next video, we're gonna do some examples of Taylor and Maclaurin series.